Hello children, today we will start this lecture from page number 7a.6, paragraph number 7a.3, equilibrium in chemical processes. Okay, so first heading is reversible reactions. So according to the definition of reversible reactions, the reversible reactions proceed in forward as well as in backward direction and never proceed to completion. So, as one hypothetical reversible reaction is given here. So, according to this reaction, A and B are forming C and D, and again C and D forming A and B. So such reactions which proceed in two different directions means from reactant to product and from product to reactant. Such type of reactions are known as reversible reaction. Okay, so for the forward reaction, A and B are the reactant, and for the backward reaction, C and D are the reactant. Okay, students. So initially, at the start of the reaction, this A and B will form C and D. Okay, it means at initial condition, reversible reaction will not start. Okay, from product to reactant formation will not start, because at the initial condition there will be no any product at all in the reaction medium. Okay, so initially the reaction will start in the form of irreversible reaction, in which A plus B will form C plus D. Then after a certain time, when a sufficient amount of C and D will form, then C and D will start forming A and B. Okay, and then only this reaction will be in the form of reversible reaction. Okay, students. Then after some time, what will happen? The amount of reactant and product become constant at a certain condition of the reaction. So at that time, rate of forward reaction becomes equal to rate of backward reaction. Okay, and that condition in the reversible reaction, when rate of forward reaction become equals to backward reaction, this state is known as state of equilibrium or equilibrium state. Okay, a state of equilibrium or equilibrium state. So as it is given with the help of graph. First graph, rate versus time. So in forward reaction, a reactant are forming product. So as the time is passing, concentration or amount of reactant decreases, and also rate of reaction also decreases. For backward reaction, with the time rate of backward reaction is increases. So at a certain time, these two rate of different reactions become equal, and that point of the reaction is known as equilibrium point, where the equilibrium state come in existence. Okay, in the B graph, time versus concentration. So time versus concentration, this is the concentration of the reactant which are decreasing with the time, and this curve is for the concentration of the reactant, and this curve is the concentration curve for the product. So concentration of product increasing with the time and concentration of the reactant decreasing with the time. So at a certain particular time, this concentration of the reactant and product become parallel to each other. The curves become parallel to each other. Means further concentration is not going to change. Okay. Further concentration is not going to change. Means amount of product and amount of reactant become constant or fixed. So when the amount of reactant and product become fixed or constant, that state of the reversible reaction is known as equilibrium state. Okay, students. Then second point, second heading is dynamic nature of chemical equilibrium. So chemical equilibrium is a dynamic state of the reversible reaction. Means at equilibrium state, the reaction from reactant to product and from product to reactant is continuing. Okay, this reaction is going on in forward and in backward direction. Means at the state of equilibrium, the reversible reaction is dynamic in nature, or you can say the state of equilibrium is dynamic in nature. Okay, students. So it is given, explained with the help of an example, with the help of Haber's process of ammonia. So according to this reversible reaction, at equilibrium state, hydrogen, the rate of forward reaction will be equals to the rate of backward reaction. Okay, and the amount of reactant and product will fixed, constant. Okay, so that state will be equilibrium state. Now if we are mixing, if we are taking some other reaction in which instead of hydrogen we are using a deuterium with nitrogen, then N2 nitrogen plus deuterium will form ND3. Okay, so we can balance it accordingly, 3 2. Okay, and after some time the equilibrium will be achieved in this reaction also. So if we mix this reaction, which is equilibrium state, with this reaction, first one with this reaction, then what will happen? The amount of nitrogen and hydrogen, the amount of nitrogen, hydrogen and ammonia which was present initially in this single equilibrium state will be present in same condition in mixed condition also with this reaction. Okay, which proved that state of equilibrium is dynamic in nature. The next heading is important characteristics of chemical equilibrium reactions. The first point, the state of equilibrium may be changed by changing the temperature, pressure, volume or concentration of the reactants or products. Okay, so a state of equilibrium can be changed by changing the temperature, pressure or volume or concentration of the reactant or products. Then second point, change in Gibbs energy at equilibrium is 0. So value of delta G will be equals to 0 at the state of equilibrium. Then third point, after the equilibrium has reached, on adding any reactant, the reaction proceed in forward direction till equilibrium is again reached. If any product is added at equilibrium, reaction proceed in backward direction. Okay, so according to this point, when we are adding amount of reactant, some amount of reactant in a reversible reaction at the state of equilibrium, then what will happen? For the some time the state of equilibrium will disturbed, but after a particular time it will be regained by the reaction. Okay, so for the time being, when we will add some amount of reactant or product, so for the time being state of equilibrium will disturbed, but after that time it will regain its initial condition. Means state of equilibrium will be re-achieved. Okay students, so when we will add reactant, more amount of reactant, then state of equilibrium will be moved towards the forward direction, and when we will add products, then it will move towards the backward direction. Okay, and again state of equilibrium will be re-achieved. The next point, in the presence of catalyst, the equilibrium is obtained quickly, but the concentration of reactants and products remains same. So presence of catalyst is not going to affect the state of equilibrium. Okay, only state of equilibrium will be achieved comparatively in less time. Okay, then fifth point, the effect of temperature, pressure, volume, concentration, etc. on equilibrium is studied by the following two laws, and the laws are law of mass action and Le Chatelier's principle. So these laws we will discuss one by one. So first is law of mass action. So according to this law, at constant temperature, the rate of a chemical reaction is proportional to the product of the active masses of the reactants, each raised to the power equal to its stoichiometric coefficient as represented by the balanced chemical equation. Okay students, so law of mass action. Mass action. This law is given by Goldberg and Wage. Two scientists was there, Goldberg and Wage. So according to this law, if A is any reactant and it is forming product, so if active mass of A is in square bracket, so active mass of any substance we represent in this way. What we do? We write the symbol or the formula of the substance inside the square bracket. It means active mass of that particular substance. Okay, so if A is forming product, it is a hypothetical reaction, and in this reaction active mass of A is this. So according to Goldberg and Wage, law of mass action, the rate of reaction of A will be proportional to its active mass. Okay students, this will be there, or we can say that R will be equals to Ka, where K is velocity constant for the reaction. Same way, if in another hypothetical reaction A and B together forming product, and active mass of A and B are A and B respectively, then according to law of mass action, rate of this reaction will be proportional to the product of the active masses of the reactant. Product of the active masses of the reactant. Okay, students? Or we can write R will be equals to K A into B, this way. Okay. Now, if again we are going to take a hypothetical reaction like A plus B, reversible sign, forming C plus D. Okay. So, according to Goldberg and Vage, rate of reaction will be proportional to the product of active masses of the reactant raised to the power equal to its stoichiometric coefficient as represented in given balanced reaction. Okay, but here this reaction is in the form of reversible reaction. So, two reactions will be continuing here, forward and backward. So, we can break this relation in two terms. Rate of forward reaction will be proportional to this value, or you can say rate of forward reaction will be equals to Kf B. Okay, where Kf is the velocity constant for the forward reaction. Same way, for the backward reaction, rate of reaction will be proportional to the product of the concentration each raised to the power equal to their stoichiometric coefficient which are given here in this balanced reaction. So, this is D, or you can say RB equals to KB C into D to the power D. Okay, so this is the law of mass action. This is the law of mass action, Goldberg and Vage. Okay, students. Then what is the meaning of active mass here? Active mass. So, active mass is equal to the molar concentration. Molar concentration, you know, molar concentration is also known as molarity. Molar concentration of the substance means number of moles dissolved in 1 liter volume of the solution. Okay, so if number of moles of any substance are N and volume of the solution is V in liter, so active mass of that substance will be equals to N upon V. Okay, and we know that value of N equals to given mass of the substance divided by its molecular mass or atomic mass. Molecular mass or atomic mass. So, if substance is molecular in nature, then this mass should be molecular mass, and if it is atomic, then it should be atomic mass. So, number of moles N will be given mass divided by atomic or molecular mass, and active mass is the number of moles divided by volume of solution in liter. Okay, so this was the law of mass action. Now we are going to discuss next page, page number 7a.8, paragraph number 7a.4, and the heading is Law of Chemical Equilibrium. Law of Chemical Equilibrium. Okay, students. So first we will derive mathematical expression for the law of chemical equilibrium, and then we will give the words a definition for this law. Okay. So if this is a hypothetical reaction again, okay, and we are going to use such this reaction number of times for the number of purpose different, so this is a hypothetical reaction. So if the active masses of A, B, C and D are respectively, then according to law of mass action, the rate of forward reaction will be proportional to product of active masses raised to the power equals to the stoichiometric coefficient, or you can say RF will be equals to KF okay. Same way for the backward reaction, rate of backward reaction will be proportional to this term. Again, rate of backward reaction will be equals to KB. Okay, students. But at equilibrium state, we know that rate of forward reaction will be equals to rate of backward reaction. Means KF will be equals to these terms. Okay, students. Or KF upon KB will be equals to C raised to the power C, D raised to the power D divided by A raised to the power A and B raised to the power B, and this will be equals to Kc. So this is the law of chemical equilibrium. Okay, so according to law of chemical equilibrium, the ratio of the rate constant of forward reaction over backward reaction, ratio of the rate constant of forward reaction over backward reaction is equals to a constant K, which is known as equilibrium constant. Okay, here we are using term Kc because this equilibrium constant in the terms of concentration. We have taken here active masses or molar concentration of the reactant and products. That is why we written here Kc. K for equilibrium constant and C for equilibrium constant in the terms of concentration. So Kc. So according to first definition of the law of chemical equilibrium, that the ratio of, at a given temperature, the ratio of rate constant of forward reaction over to rate constant of backward reaction is equals to a constant which is known as equilibrium constant. And we can define this relation in other words also. The ratio of product of products raised to the power equals to their stoichiometric coefficients over to product of reactants raised to the power of equals to power of stoichiometric coefficient of the reactant equals to constant. Okay, students. So in these two terms we can write law of chemical equilibrium. So this is law of chemical equilibrium and its mathematical expression. Then we can break this relation in two forms as Kf upon Kb equals to Kc, or C to D upon A B to B equals to Kc. Okay, so these are the two ways in which we can define law of chemical equilibrium. So according to this first mathematical expression, equilibrium constant is the ratio of rate constant of forward and backward reactions. And according to this relation, that at a given temperature, the product of concentration of the reaction products raised to their respective stoichiometric coefficient in the balance chemical reaction divided by the product of concentration of the reactants raised to their individual stoichiometric coefficient has a constant value K. Okay, and this K is known as equilibrium constant. So equilibrium constant K we can write in two different terms. In the terms of concentration, then it will be Kc, or in the terms of partial pressure, then it will be Kp. Okay, students, Kc and Kp. So Kc in the terms of concentration and Kp in the terms of partial pressure. Then we will discuss this Kp, equilibrium constant in the terms of Kp, partial pressure. So equilibrium constant Kp in gaseous systems. So when we write equilibrium constant K for any gaseous reaction, then equilibrium constant we give the term Kp. Okay, for example, H2 plus I2 are forming 2Hi. Okay, students, so in this reaction all the reactant and product are in gaseous phase. So if the partial pressure of hydrogen in the system is pH2, partial pressure of iodine in the system is Pi2, and partial pressure of Hi in the system as Phi. Then according to law of chemical equilibrium, Kp will be equals to Phi product in the terms of partial pressure divided by reactant in the terms of partial pressure. Okay, Kp will be Phi to the power 2 divided by pH2 into Pi2. Okay, now one more example for Kp. N2 plus 3H2 forming 2NH3. All the reactant and product terms are in gaseous phase. So we can write the law of chemical equilibrium or the relation of K in the terms of Kp for this reaction. Okay, so Kp for this reaction will be equals to PNH3, where this PNH3 is the partial pressure for ammonia raised to the power 2 divided by PN2 into PH2 raised to the power 3, because stoichiometric coefficient which are present here are 3 for hydrogen and for ammonia is 2. Okay, so in this way we will write the equilibrium constant Kp in the terms of partial pressure of the given gaseous reactant and products. Thank you.